Das ist der rosa Motor, or the pink motor. So Harmonic Drives Germany has this little pink motor, geared brushless with SSI encoder that seems to be more and more popular. I've seen it a couple of times, checking it out on their webpage. It's pretty cool. They do list all the data. There's options for feedback like NDAT 2.2 and some other very Germanic type feedback devices. So we're going to take a look at how to wire this SSI encoder up to the drive. So I'm looking at the encoder guide from our webpage, and it talks about how to hook up the clock coming from the drive, X and X naught, goes out to the encoder, twisted pair shielded, shield connected to frame. So we clock out, and then we get the data back. The data comes in on the S naught on the Copley, so on the data port. There's a +5 and a ground. The feedback device has 2 sensor wires too that you could double up with the +5 and the ground. That's fine. Just double up the pins there. That allows you to get longer distance of transmission. We'll take a quick peek at the feedback connector here. We've got the CHA-14 and 17 come with the M128 feedback device. That's the SSI option. You have a UV and a W, ROT, Schwartz, and WIBE. So red, black, and white. There's an optional brake plus and brake minus, Schwartz, and white again, WIBE. There's a protective earth, grün Gleb, green, yellow, and so that's the motor power wire. And then you can see the feedback connector here, the M128 signals. We're mostly interested in the ground, the Schwartz, pin 7 and 15, the clock, the white on pin 14, the clock minus, blau or blue on pin 5, data, grün or green on pin 3, data minus, WIBE, white on pin 13. Now there's also a sine and a cosine. We don't need to connect that. The SSI is fast enough, but you can connect that to sine cosine if you want. It's just not used by the Copley, but could be later if needed. There's also a sensor ground and a sensor positive. These are 2 extra wires which you could run down to the motor feedback or device to get extra gauge thickness, less IR drop for long distances. So it's okay to hook those up to +5 and ground at the drives, +5 and ground. And we'll also take a look at the motor specification. So CH-14A, I just searched in the document for resistance. So 0.4 ohms, inductance 0.35, rated speed 8,500 at the motor. At the output, it's 100-to-1 gear. The current should work out to be 3.1 amps RMS continuous. You can put the peak and continuous torque in, but divide by 100, and the motor torque constant 0.04 Newton meters per amp RMS, and that gives us a back EMF voltage of 3 volts per kRPM. So this is like a 48-volt motor. So we'll step through quickly on the configuration of this, and it's a brushless rotary with SSI on the motor. And we can put it in a CAN mode, which is fine. Emulated output's cool. We'll look at the specification for the CHA motor with the M128, and we'll see it's 17 bits, 13072 counts per rev. It's 12-bit multi-turn for 4096, so 17 plus 12-bit is 29 bits. It's a binary format. and there's no options by default, and everything seems to work just fine. If it has a break, you could put a stop time, a low speed, and a delay time for disable. Come to a safe stop and hold. I grabbed the data. There's the resistance, the inductance, the torque constant. Here it is in Newton meters per amp RMS. Here it is in peak. Volts per radians match up. Data looks good. Divide the peak and continuous at the output shaft by the gear ratio, and you got some peak and continuous torques. You got some inertia. It's 5-pole pair or 10-pole motor, and it's 8,500 RPM. Tuning gave some pretty good current loop limits. We calculate from this, we get 4.3 amps. So just looking at the calculated values here. So 4.38 amps peak is the same as the 3.1 amps RMS, a long time at peak. With another drive, I could get more current. Current loop bandwidth should be about 1 kilohertz. Velocity limit, let's not cut ourselves short, so let it go up to the top speed. It's warning us based on our 26-volt supply, but if you use 48, you could probably hit it. You got to tune it, crank the gains up. I move my velocity loop filter pole to a single hertz, get a little more bandwidth out of it. Not necessary. Its calculated values are pretty good. We get normal gains here and some normal XL and D cells for some testing there. One thing we need to do before we can make any moves in tune is enable the drive. So we got to put the stow in. I'm still hardware disabled. Pull the input to ground. I'm hardware enabled. I can enable, but I'm in a CAN mode waiting for the master, so nothing happens. I can jog, and that enables the drive. So we can make some moves. And hopefully we'll have an opportunity to show some tuning with the pink motor. Das Rosa Motra. Okay, so we're going to take a quick look at phasing and tuning. Under tools, manual phase, I can enable, and if I press and hold the forward, I'm rotating a current vector, but you can see the feedback's not following. So if I don't deliver enough current, then the feedback cable doesn't get to move very much, or the feedback device. So we need to overcome static friction. So I'm going to use something closer to the continuous current rating of this motor to get it to move with it. Now there's some constant friction, so there's a lag. If I try to boost up the current, so as you see, I've got good phasing in both directions. If it was going the wrong way, you could invert, so they should go the same way. If you had a big offset, there's a wicked lag and a wicked lead. So I think my other motor was 150 with the SSI, but this one's wired a little differently, but that's okay. So should have wired in a logical manner. So again, when you go forward, right, counts need to go, don't press this encoder 0 button. That will rephase the motor and we'll have to send it back to the motor manufacturer. So now we have proper commutation, and we can take a quick peek at the tuning. So apply to the current, auto setup checkbox, hit start, commanded in magenta, blue in actual in blue. So that's good current loop tuning. We could adjust the gains if we had to, but that's good. Velocity loop, you can do parameter limits. So maybe that's a wicked high acceleration with a load, so let's shorten it, turn the frequency down a little bit. But basically we can just do the auto setup and let it hit start, and it's sort of bang, 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 back and forth, pretty good settling for the actual velocity, so that's good. I think that's just from the calculated value. The auto setup checkbox does profile velocity and following arrow. I'd also like to look at actual current and do a distance of 131072, which is a single turn at the motor, inside the motor. So 100 to 1 gear, that's 1/100th of a rev. I'm going to do a little repeat and reverse with a low trajectory here, and we should watch it bang back and forth. So we're doing little profile moves, accelerate, run, decelerate, stop, a little following air. So this was tuned rather nicely for velocity. You know, if your integral's too low, you'll get some steady state error. The integrator starts, yeah, there's a 50 counts of steady state error. The integrator will bring in the blue following error to closer to 0. So give it 1,000. Takes a little time to get there. Maybe give it 5,000, and it gets there quicker. Over integrate, and you'll see some hunting and really, you know, overdoes it. So this is a little dependent on the inertia. If I had a huge inertia on this motor shaft, I might want to have a little bit more. But it's 100 to 1 gear, so the reflected inertia brings things way down. And then I bumped up the proportional a little bit to give me a little better steady state, a little less following error. But, you know, if the PP is too high and your inertia is big, there'll be a little bouncy going on there. That's the electromechanical time constant there. And we can take a look at left click, drag, drop. We can see the profile move and take some measurements. So to make this move, required an RMS current of 0.8 amps. That's fine for this motor and for this continuous current of 1 amp or 3 amp, whatever the motor is. So this should be less than the continuous current of the Copley. The following error is good. I noticed the current on average is about 0.47, but right here you can see it's about 0.5 amps. 0.5 amps while we're moving. So there's like a continuous friction. So it's not just stiction to overcome and accelerate the inertia, but there's actually a constant friction. So if this was a torquer and we needed like 1 amp of torque, we'd have to add at this speed 0.5 amp to the 1 amp we wanted for the rated torque at the output, because this is like just a friction. You know, that's without actually measuring at the load, so maybe a load cell or a dynamometer could do a better job measuring torque at the output. But I can see here that we're just wasting some current delivering some rotation of the motor, so that should just be friction. Okay, be sure to save to a disk and save to flash your changes. And thanks for checking out the pink motor.